will be presented by Maurice Dekker and its work with Gregor Behnke.
Right, the title is very long, but a shorter title could be Fixed Length Planning, in my head at least. And it's a pure theory paper. First, I recap classical planning. So fully observable deterministic planning. In this planning problem, it's basically pathfinding. There's a truck that needs to drive to a building to deliver a package, say. And a plan for this problem is, for example, to drive to node B, then to C, and then to E. All right? But this is an equally valid plan. We are not interested in optimal planning in this paper. You could also drive to B, C, D, and only then to E. Okay, what is fully observable non-deterministic planning? Let's modify the example. Now there's a traffic light at B that we can fully observe, but we don't really know the policy of the traffic light. So at the time we arrive at B, it might jump to any color. So we don't know in advance what the color of the traffic light is going to be. Then normally we solve these sorts of planning problems with branching plans. Here, a valid plan is this, for example. We drive to B. If the traffic light is green, there's no issue, and we drive to C and then to E. If the traffic light, on the other hand, is red or orange, we execute a wait action, and assuming that the traffic light will be green after that, we then proceed in a similar way. Now notice that this plan has two branches, and one branch has 3 actions, one branch has 4 actions. Okay, the idea of our paper is to rule this out. What if we want a plan where every branch has the same length? And we don't care about what length, but we want it to be some length that's the same for all branches. So you might ask, okay, in the first place, why on earth? In this example, imagine that there's no parking space at E. So the truck needs to drive to E to deliver something, but it cannot wait there. It has to basically throw the package out of the window. And on the other hand, the person receiving the package has very valuable time, like precious, it's maybe a very rich person who doesn't want to wait. Then how can you solve it? Basically, the only way to do it is if the truck driver says in advance, I'm going to deliver the package at 3 o'clock. So then the receiver knows when to go down and receive the package, doesn't have to wait, but also the truck driver can continue driving, which was necessary because there was no parking space. Okay, that's a motivation. And in this example, we can do it in this way. So fully observable non-deterministic planning with exact plan length. This is an equally valid branching plan, but now every branch has 4 actions, and that would be what we're after. Another example. First we go back to classical planning. Suppose we want to run tasks on a cluster. This is a picture from the cluster close to our university. And we make some assumptions that we can only access 1 core, and we need to say ahead of time when we're using the cluster. So we kind of need to book our computation time. And an example of tasks could be that we want to use the cluster to help us prove some theorem. This might take 2 hours, and there's another task that is to work on the search for extraterrestrial intelligence. But the goal is just to prove the theorem. So SETI is nice, and we can do it, but we don't need to do it. So then a valid plan is just to prove for an hour, prove for another hour, and the theorem is proven. That was the goal. But this is also an equally valid plan. Like I said, we're not doing optimal planning. So let's say we can also spend an hour on SETI just for fun. Or do it twice, even. And again, let's look at a non-deterministic version of this problem, where we don't know in advance how long it's going to take to prove the theorem. We might be fairly sure that it's true, but to verify everything could take either exactly 2 hours or exactly 4 hours. Then a valid branching plan is this, where we start proving the theorem for 2 hours, and then we have a look. It's fully observable, so we can check, is the proof done? Then we can exit, and if the prover is still busy, then we prove for 2 more hours, and we reach the goal, we prove the theorem. But this is not desirable because we need to book our computation time in advance, so we need to book 4 hours to accommodate for the worst case. And that means if we only need 2 hours, then 2 hours will go to waste. So this is the one branch has 2 actions, one branch has 4 actions. This is then kind of better. If we are done after 2 hours of proving, let's not waste the remaining computation time and spend 2 hours on SETI. And this is then a branching plan with exact plan length. Every branch has the same length, which in this case means we know how much computation time to book in advance exactly. Yet another example might be giving a presentation, because then it is fully observable and a bit non-deterministic, because the audience might react in a certain way that influences the presentation. And it could be that you have a choice in how long your presentation is. Well, in this case, it's sort of fixed to 20 minutes, but it could be that you have a choice as long as you tell the organizer in advance how long your presentation will be, so that they can schedule it, right? So you can choose how long your plan for the presentation is, but your presentation needs to be exactly that length, otherwise there's going to be a very long, awkward silence, even longer than the ones in my talk. Okay, so the results about this type of chosen length planning. Okay, this is an existing result about normal font planning. That plan existence is X time complete. And with our new criterion that every branch has the same length, you might think it's similar or even easier because you're more constrained in the type of plan you could try to construct. But our result is that it's actually harder. Sorry, I'm mixing it up. The reason why font planning is X-time complete is you can regress from the goal. So you have the state space and you have all the states that satisfy the goal, and then you can regress from what states can we reach the goal, and from what states can we reach those states, from what states can we reach those states, and so on and so forth. And this set converges, and then you check if the initial state is in that set. That's how you do it. Okay, and then what I actually want to say, our version, the fixed length or chosen length font planning is harder, X-space complete. And the previous proof doesn't work anymore because you're now interested in the length of the plan. So a state doesn't carry all the information anymore. You don't just care about the propositional variables, but also about the length. So you don't need to look at the state space, you need to look at the time expanded state space. And then you can proceed in a similar way. So you have the goal, and you can look at all the states from which you can reach the goal with one action, exactly. And then you can calculate from that the set of states from which you can reach one of the previous calculated states in exactly one action. And you can do this inductively, so you only need to remember the last set of states that is exponential in size. And this is an X-space algorithm. Oh, when do you stop? You stop at double exponential plan length, because at that point you must have seen the same set twice, and then you're going to end up in a loop if you haven't solved the problem. So that's kind of how you prove membership. And hardness, we do a Turing machine reduction in the paper to a kind of game that is equivalent to this form of planning. Moreover, we have an application to HTN planning. So there exists a bit of work on font HTN planning. And one version is called fixed methods font HTN planning. And then if you restrict that to regular problems, there's a result by Chen and Berger that it's in X-space, and we prove hardness for that. In fact, we prove it for an even more restricted fragment of HTN problems. So regular fixed methods font HTN planning is X-space hard, but also loop unrolling, as we call it. Regular fixed methods font HTN planning is X-space hard. It's kind of, you have only two methods, basically. That's our further restriction. So this table of HTN font complexity becomes a little bit more complete. To conclude, fixed length font planning is X-space complete. Regular fixed methods font HTN planning is X-space complete. In layman's terms, calculating a deterministic plan length in a non-deterministic environment that has high complexity. Thank you for your attention.
Thank you for your talk. And thanks for advocating the search for alien life. I like that. Any questions? I have many.
SETI is not running anymore, unfortunately, but
so I assume that the motivation for the first was actually the second. So I wonder what made you start looking into this. I would assume that you wanted to prove the open result in HTN planning, and you discovered the other variant as a fitting match. Is that right?
yeah, that's right.
Oh, that's good. That's wonderful. Do you know if you just have an upper bound for, like, rather than the that every single branch has the same, but to give an upper bound on the problem? I would assume it's still X time. Do you know that? So you're demanding that all the branches have the same, right? And if you just do like a length-bounded planning systems, but in the font setting, and then you can still have different lengths, I would assume that's still X time. Do you know this? Is that known?
Oh, so just cost limited cost.
Yeah, you can call it costs. I would say make span, but yes, number of actions, plan length basically, but without your extra constraint. Because I don't know whether that's known in font and kind of closely relates to what you have done.
That's interesting. I don't know.
Okay, that's fine.
Just based on your the quick proof that you've shown, I think they must be the same. Your dynamic programming approach to calculate one step and then second step based on the first step, wouldn't that imply that it is the same hardness for that question? So if you show your proof slide?
Yeah, I think that shows that it's in X time, right?
Yeah, in X space.
X time even, right? Because then you know you can stop at 2 to the power input.
Yes. Yes.
So you can stop earlier. So it's that makes it X time. And probably also and should also be X time hard. Yeah.
Yeah, Hardness for this, I think. Any other questions? Yep.
Yeah, actually, so I just thought about it because of the lengths and things. So
does everybody hear him because we have a microphone?
Oh, sorry. Am I too quiet?
No, you're good.
Oh, I was looking. You're halfway. The other half? Okay, great. Yeah. So these lengths are, and even from your example, you were counting the number of actions as like your fixed length. But I guess I'm thinking because you gave the example about the PowerPoint presentation, which is looking on a scale of like time, and then you were talking about scheduling as another example, and I guess I'm thinking then about like time and all those other factors maybe being more of a cost-based thing instead. And maybe there's already work in this, and I apologize if I'm missing it, but is there a way that you can do like fixed costs instead, so they might have different action lengths, but then the costs would all still work out? Will that still work then for this kind of method of checking, or would that change the assessment of like complexity?
We're doing strips, so theoretically you can calculate rational costs. You can compile rational costs into unit costs, and then it's equivalent.
Yep, I didn't think of that. Thank you.
Okay. I haven't thought about irrational costs.
We would have time for one more. There's more. Do you have an idea of how one could actually solve that? Because for the HTN setting, there's also no solver yet. So do you have an idea how you would approach solving the problem? The font setting, the non-hierarchical font setting with equal length?
So you want to try to modify existing font planners.
Yeah, for example, or any combinations that you
Yeah. And you want to try to prune away extra parts of the state space. maybe using operator counting techniques, you could estimate that if you go to a certain state, then definitely you will need at least 3 times action A, and if you go to another state, you will need at most you can only do action A twice, and then if you can't rule out that you go to both, yeah, then you could maybe compensate with other actions. So yeah, we haven't found anything great, but probably the best shot is to extend existing font planners.